Okay, so just quick thing. So the midterm is coming up next week. The practice problems have been posted for a little while now, and so this week's PSO will also largely be midterm review as well. Besides, maybe poking at some things we also cover this week. Okay. The big basketball tournament. Yeah, question.
So is that, I remember for midterm 1, the Tuesday before the midterm, our lecture was still a midterm review. So is next Tuesday still going to be a midterm review, or is this the only way to do it?
It doesn't have to be the only way, but I hope you guys go. If you guys want me, I can show up on Tuesday again, but I'll do something different if I did come on Tuesday. So it'll be disjoint. Okay. Okay. All right. So where did we leave off? We have been going on a binge of graph algorithms before spring break. So that started with spanning trees, and then we did edge disjoint paths and max flow and min cut. In fact, last time we just did applications of max flow and min cut, which is pretty fun. My goal always in the week before midterm is not to introduce, dramatically different things. So I try to pick something similar. So today we'll talk about faster algorithms for some of these problems in the special case of undirected graphs. Okay, so all the max flow min cut stuff we did last week, 2 weeks ago, worked in directed graphs. But we'll see that we can leverage a little bit more symmetry in the undirected graph. There's a little bit more structure. And one reason I also like this topic, this particular topic, is that one way we're going to get faster algorithms in these undirected graphs is to actually use spanning trees. So we'll get some kind of crossing of topics. Okay? All right, so let me first introduce this problem, the global minimum cut. So previously, we used to always, we did a lot of ST min cut. So that means, we have two vertices and I try to find the maximum number of paths from S to T or the minimum number of edges to split up S and T. Okay? Now my goal is just to split up any pair. Okay? So just a generic cut, not necessarily an ST cut for a particular S and T. I just want to remove the minimum number of edges so that some pair, at least one pair, becomes disconnected. So this, as presented, is a completely connected graph. The goal is to delete as few edges as possible so the graph becomes disconnected. Okay? So I'll give you guys 30 seconds to stare at this. What is the minimum number of edges you need to delete to disconnect this graph? Did anyone get 5? Okay, what would be one was 5? Yeah.
You could just delete all of the edges from the middle vertex, and that would just leave the middle vertex disconnected.
Okay, so yeah, one reasonable strategy is just to identify, say, the minimum degree vertex. This one is degree 5, and I could remove all the edges incident to it. This is actually called a singleton cut, in the sense that one side of the cut is just one vertex. A set of 1 is sometimes called a singleton. Okay, did anyone do better than 5? Obviously, I've set it up so it's hard to see, but it'll be easy to recognize the solution. Yeah.
Is the removing all the edges from the min degree vertex not like a guaranteed thing that'll work? Or the
That's right, that's right. So I'm suggesting that maybe there's a more sophisticated cut than just the minimum degree. Minimum degree will always give a cut, and I guess I'm asking if you can do better. Yeah.
I kind of see this graph as like two pentagons, and if you remove the two smallest edges, the one on the very bottom and then the one on the very left, and they're both like kind of small, that seems like it would be.
Okay, so this was a trick. I took two dense graphs and overlaid them on top of each other and then barely connected them by two edges. So the two dense graphs themselves have very strong connectivity, right? They have very large minimum cut because everyone's connected to each other, but there's this bridge of two purple edges. Okay, so the minimum cut here would have been 2, which is less than the minimum degree in the graph. Okay. So yeah, even with 12 vertices, this problem can be tricky. All right, so okay, so we want to find some algorithms for computing the minimum global cut. What is maybe one algorithm that you guys could already come up with based on the tools you already have? If I wanted to compute the minimum global cut. Yeah.
You can just do it for each ST walk.
Okay, so we can try, all pairs S and T, compute the minimum ST cut, and do that for all pairs. One of those pairs would have been separated by the minimum global cut, as long as I picked one from red and one from green. So I guess it depends, if I had picked S and T incorrectly, so here S and T are from the same click, we wouldn't have found a very good min cut, but they were separated, that minimum ST cut. Or if they were in kind of the opposite communities, the S and T cut would have been the global minimum cut. Okay, so that'll take something like n choose 2 max flows for whatever the max flow running time is. I think the best one we have together is m squared n. In the homework, you'll do one that's maybe slightly faster for polynomial-sized flows. Okay, so that would take n squared max flows, right? One for every pair. Can anyone do better than n squared max flows? But still using max flows? Yeah.
Is there a way that you could reorganize the graph into a bipartite situation so it'd be easier to know what's connecting to how many components?
Yeah, is there... I think that's hard in general. I mean, first it was not easy for you to see it. It was a 12 vertex. Second, this isn't although there is a natural pattern of two kind of subgraphs, this is not actually a bipartite graph either. So, no, that's going to be tough. So you're not really, it's actually simpler. It's similar to the n choose 2 max flows. I'm really asking, can you figure out how to do it with just n max flows? Keep in mind it's an undirected graph. Currently n choose 2 tries all pairs. Can you get n? Yeah. Maybe if you added a source vertex, close, it kind of. There's something, there's a trick. Okay. Maybe you don't have to try all pairs S and T. Maybe you can just fix S and then try all T. Right? So whatever the global min cut is, S is on one side or the other, and then you just have to get T from the other side, and then you'll get the minimum ST cut, right? So in this example, we could have, fixed S here, and then we'll try all sorts of different T's until we get one that reveals the minimum global cut. Okay. All right, so you can do a little bit better than choose two pairs. You could get n max flows by fixing S and looping over all choices of sinks. Similar in spirit to introducing a super source, but it's more like fixing a single source. Okay. All right. Anyway, so you can reduce global min cut to a bunch of ST min cuts. Our fastest ST min cut, strongly independent of the size of the cut, is still m squared n among the algorithms we've done together. Okay. So here, then, we're going to discuss a different way to compute the minimum cut, which for the time being I'm calling a mysterious minimum cut algorithm. Okay, that's going to take roughly m squared time. We'll go through it slowly. Okay, but that's actually faster than a single ST cut as far as we know how to do ST cut flows, and it's much faster than n ST cuts, or n squared ST cuts. Okay, so it's a recursive algorithm. Okay, I'm going to walk through a code and then I have some examples coming up. But if there's two vertices, then there's nothing to do. We just return whatever separates the two vertices. Okay. Now here's sort of the bizarre step. We're going to produce an ordering of vertices, v1, v2, through vn. Okay, where v1 is chosen arbitrarily. Okay, and what we'll do is, when I'm choosing v2, I'm going to look at v1 and see who has the largest weight edges to v1. Okay, so v2 is going to maximize the weight of edges to v1. Now when I'm choosing v3, I'm going to choose a vertex that has the largest kind of capacity of edges to v1 or v2. Okay, so I'm going to choose these vertices one at a time in sort of a bizarre, greedy fashion. So maybe I've chosen 10 vertices, and the 11th vertex, I'm going to try to find that vertex with the most edges going back to the 10 I've already selected. We'll walk through an example, that'll make it more clear. Okay? And what that'll do is that'll give you an ordering, v1, v2 through vn. Again, not at all clear why this is a good idea. Okay? Now the last two vertices, right? Vn minus 1 and Vn. What we're going to do is we're going to contract those to a single vertex. Okay? Obtaining some other graph G prime. I'm going to recurse on G prime, which will give me some cut. Or I'm going to compare that to the cut that's only Vn on one side. Okay, sort of a bizarre algorithm. Okay, so here then is here's an example. Okay, so in this graph, what's the size of the minimum cut in this graph? 2. Okay, so those two give you a minimum cut. Okay, so all right, so let's number these vertices. I want to be a little bit consistent with what I wrote in the notes. we're going to do this numbering thing. I'll start like this. I'll start with V1 here. And then, okay, V2. And then I got to pick some vertex that has a lot of edges to V1 or V2. So this could be V3. Okay. This would have to be V4. Okay. V5. Okay. V6, because it has 2 edges. Everyone else left had 1 edge. The rest is arbitrary, so V7, V8. Okay, so that would be one example of a greedy ordering. Okay. And so, okay, what the algorithm will do is say, okay, let's first look at this cut, which has 3 edges. Okay. That's one of the cuts it'll think about. And then it's going to take these 2 vertices and contract them into one. So, alright. This gets boring. I've already kind of laid out the rest. Okay, so if I sort of contracted V7 and V8 together, it ended up looking like this. Okay. Except those 2 contracted edge, the contraction at some level has, now there's sort of 2 edges like this. Okay, so I squeeze V7 and V8 together, and sort of those, now we have sort of 2 copies of edges going to that combined vertex. Okay, so I'll keep calling it V7 because it's nice because it preserves the numbering. But V7 in that second picture really represents 2 vertices in the original graph. Okay. All right. If we number the vertices again, actually the same numbering would still be okay. One can inspect, so I don't have to rewrite it. Okay. In which case, I would then look at this cut. This is the last vertex. Okay. This is a cut of weight 4. Right? Okay. And then we would contract these 2. Okay. Okay, so if I contract those 2, we can work off this graph. What will I end up with? So we already were like this. Okay, so it might end up like this, where now this has become an edge of weight 3, if I'm not mistaken. Okay, so secretly this bottom right vertex represents 3 vertices in the original graph from a bunch of contractions. Okay. All right. We can number this again. V1, V2, V3, V4. I think that's all fine to this point. V5, V6. Okay. So then now the algorithm looks again at the singleton cut induced by the last vertex in our numbering. So that's a cut of weight 4 again. Okay. And it's going to contract these 2. Once we contract those 2, now our graph will look like like that or something. Yeah, it'll still look like this. Okay. And that numbering would still be okay, so I won't renumber them. But now you'll see that the last vertex, which corresponds to really 4 vertices in the original graph, if you undid all those contractions, actually does find that minimum cut of size 2. Okay. And then it would keep going. It would contract these 2 because they're the last 2 vertices in this bizarro numbering system, and so forth. Okay, so somehow it keeps doing this weird greedy ordering, looking at the last vertex in a greedy ordering, looking at sort of the cut was just that vertex in a contracted graph, and then contracts the last two and keeps going. Okay, and not at all a reasonable algorithm. So here, instead of boring you, I've already drawn some out. I should have had a red line here. Okay, so the algorithm will, last vertex contract, last vertex contract, last vertex contract. Oh, it finds the min cut here, but then it'll keep contracting, and it'll look like this, that, and that. Okay, so keep doing this numbering, keep looking at the last vertex. The whole execution, I guess, would have looked like this. Here I'm going from left to right, top row, then second row. Kind of fun algorithm. Not at all clear why it worked, or why it should work every single time. Okay. But is the algorithm make sense? Just the raw steps. Okay. All right. Okay. So here are two claims to try to understand this algorithm. I'm going to use the following notation both in this section and the next one. So I think we used this before. I'm going to let lambda st denote the connectivity between two vertices s and t. Okay. And then I'm also going to write lambda g to denote the minimum cut of a graph g. Okay. Okay. So now our algorithm either looks at this last cut, or it'll recurse on that graph obtained by recursing after contracting the last two vertices. Okay, so that was G prime. So the first claim is that lambda, the global minimum cut in the original graph, is either the minimum cut separating the last two vertices, lambda Vn minus 1 Vn, or a cut in the original graph, or in the contracted graph. Okay, so either the minimum cut separates Vn minus 1 and Vn, or it'll be a minimum cut appearing in that recursive subgraph. Okay. The other claim is that for this particular ordering, the connectivity between those last two vertices is equal to the weighted degree. This all works for weighted graphs, so my example is unweighted. The weighted degree of the last vertex. Okay, so the claim is that checking that last vertex and its cut induced by it, the singleton cut, gives you the minimum Vn minus 1 Vn cut. Okay. All right. One of these claims is easier to prove than the other. Anyone see why either claim would hold true? Yeah.
I'm a little confused about the ordering. I'm not really sure how we could. I guess I'm confused about how the two claims work if we don't know which vertex is n and which vertex is n minus 1.
So this is particularly the ordering generated by the algorithm. So it's greedily doing the pick one vertex, pick the second vertex to have the highest number of edges to v1, pick the third vertex to have the largest number of edges to v1 or v2. So it keeps picking sort of this maximum. Actually, one of these claims doesn't really have as much to do with the ordering, and the other one strongly depends on the ordering. The easier one is the one that doesn't depend on the ordering so much. Anyone want to guess? You have a 1 in 2 chance. Oh yeah.
I think claim 2 doesn't depend on the ordering.
Okay, so claim 2, well, claim 2 is actually not necessarily, so if it didn't depend on the ordering, if it was just, then we're really saying that the connectivity between two arbitrary vertices is equal to the degree of one of them, which is not generally true. I mean, we had a minimum cut that wasn't the minimum degree as well. So actually this one does require ordering because it's just not true in general. But let's look at this one. Maybe this one's a little weird because contracting two vertices is weird to think about. Okay, but what's going on? Okay, so Vn minus 1, okay. How it goes. Somewhere in the graph there's the minimum cut, right? There's some minimum cut separating the vertices. Now, Vn minus 1 and Vn are either on different sides of the cut or the same side. Okay? So, if you had Vn minus 1 on one side and Vn on the other, okay, then the connectivity between those two does give you the minimum cut in the entire graph. Okay. On the other hand, if they were on the same side of the minimum cut, right? So originally they're two different vertices, there's different sets of edges, right? But if I collapse those two sort of into the same vertex, right? They have some mega vertex that combines the edges. The minimum cut doesn't change. It's still the same edges going across the middle. So if they're on the same side of the cut, it's okay to contract them. The cut won't change. If they're opposite sides of the cut, then they are an ST pair that would give you the global minimum cut. Okay? All right. Okay, so that one is not too bad. But claim 2 is really the mysterious one and the one that requires this ordering. Okay? Claim 2 is saying that if you do this weird, greedy ordering, then separating the last two vertices, the minimum cut between the last two vertices is just has the last vertex on one side, okay, which is not true in general. Okay, so alright, but if we had these claims, so it'll take a little longer to prove claim 2. If we had these claims, then why would the algorithm then be successful? I assumed in particular the second claim was true. Yeah.
Is it because
Yeah, okay, so the algorithm, on one hand, when it recurses on the contracted graph, it's going to get you, by induction on number of vertices, we'll assume it works on smaller graphs, it'll get you the connectivity of this contracted graph. And claim 2 says, well, this singleton cut, that is a connectivity between the last two vertices. That's the minimum cut between the last two vertices. And claim 1 says, well, the global minimum cut is one of these. Okay. So really, claim 1 wasn't as hard to show. So it really comes down to why on Earth would the minimum cut between the last two vertices of this bizarre ordering be induced by just the last vertex on one side. Okay. All right, so that's what we have to prove, and then we're done. Okay. All right. So there's a name for this ordering, at least by the authors of this minimum cut algorithm, Nagamochi and Ibaraki. They call it maximum adjacency ordering. Sometimes I get lazy and I just call it greedy ordering. But the rule is that VI, the ith vertex you choose, maximizes the number of edges, or maybe the total weight of edges, from VI to, I'll introduce some notation, I'll let S sub I minus 1 be the first I minus 1 vertices that were already selected. Okay, we're just giving a name to this loop that appeared in the middle of the algorithm. Okay? And you can do this quickly with Fibonacci heaps, where you're just keeping track for each vertex. You've already taken 10 vertices, and then you have n minus 10 vertices left. And you want to figure out which of these vertices has the most edges to the first 10 vertices. Right? So we can have a heap that sort of keeps this score. And when I take that 11th vertex, I have to add the new edges to the remaining guys. So for each edge in the 11th vertex, I'll update the value in the heap in constant time because of Fibonacci heap. Okay? I pay log n whenever I remove the next vertex. So you can do this in n plus n log n times. So you can do this ordering very fast. In an unweighted graph, you can do it even faster. There's kind of various linked lists. Okay. All right. Yeah, it's so simple. Maybe it's not too surprising that you can do it very fast. Okay. But the algorithm itself just calls this ordering n times, right? It starts with the original graph, orders the vertices, does a contraction. There's one less vertex, does another ordering, does another ordering, does another ordering. There's only n orderings because each one gets rid of one more vertex until you get to an empty graph. So running time, mn plus n log n, or mn plus n squared log n, is just doing this ordering in each of those contracted graphs. Okay, you have to redo the ordering. The ordering can change. Okay. All right, so in terms of these quote-unquote MA orderings, okay, Okay, all I've done is I've taken our algorithm and I've replaced that loop, and I just call it an MA ordering from now on. We're going to study the properties of one of these MA orderings, maximum adjacency orderings. And I've renamed the algorithm to MA min cut, because that's how I think of it. Okay. So the claim is really saying that the last two vertices in this maximum adjacency ordering have this feature that the minimum cut between them has just the last vertex on one side. Okay. So the key claim in terms of this ordering again is that the last two vertices, their connectivity is given by the degree of the last vertex, weighted degree. Okay. All right. So let me set up the lemma. Okay. So here I've written down some vertices, in MA order, V1, V2, Vn minus 3, Vn minus 2, Vn minus 1, Vn. Okay. So what I want to do is I want to think of, I'm going to call this whole set of vertices Sn minus 2, the first n minus 2 vertices in ordering. Then we have 2 vertices left. Okay. And, okay, I'll introduce some notation. So I want to think of, I'm going to let this purple line, you can think of Sn minus 2 as being one vertex even. In this proof, they won't be distinguished. Okay. I'm going to let A represent the weight of all the edges from Vn minus 1 to the preceding n minus 2 vertices. Okay. I'm going to let B, draw like this, represent the weight of all the edges from Vn to the first n minus 2 vertices. Okay. And then I will let C represent the weight between the last 2 vertices. Okay. So, for example, just to get some sense of the notation, I know that because Vn minus 1 was chosen before Vn in the ordering, I immediately know that, for example, A is bigger than B. Because Vn minus 1 was supposed to have the most weight to the preceding n minus 2 vertices. Okay. The weight of this cut in this notation is B plus C. Okay. So the claim we're trying to show is that the connectivity between Vn minus 1 and Vn is exactly B plus C. There's no better cut out there. Okay, I'm just establishing notation. Okay. And we're going to break the analysis into 2 cases. The first case is when C is equal to 0. So the first case is when there's no edge between the last 2 vertices. Okay. And the other case is when there is an edge between the last 2 vertices. Okay. Okay. Alright, so that's a setup. Let's look at the first case when C is equal to 0. So I'm going to erase this edge. Okay. So I'm just down to A and B now. There's no edge between Vn minus 1 and Vn minus 2. Okay. And in that case, the degree of Vn is now just B, and the claim is that this represents the minimum cut between Vn minus 1 and Vn. Okay. All right. So the first thing we're going to do, I believe this was a PSO problem, okay, is we're going to point out that the connectivity between Vn and Vn minus 1 is at least the minimum between, make sure I get it right, okay, either the connectivity between Vn and Vn minus 2, or the connectivity between Vn minus 2 and Vn minus 1. Okay. So Vn minus 2 is sort of being used as the middle in that triangle inequality sense. Okay. Alright, so what does that get us? That means that if I want to show that this quantity is at least B, it would suffice to show that each of these is bigger than B. Okay, and we'll do one at a time. Okay. Alright, so let's look at the first one. I want to show that the connectivity between n minus 2 and n minus 1 is at least B. Okay. And what we're going to do is I'm going to think about the graph where I get rid of Vn. So think about the graph induced by just the first n minus 1 vertices. I guess I'm calling that G sub 0. Okay. Now, what's convenient about these MA orderings is that, okay, I've ordered the numbers from 1 to n, right? But now I'm ignoring the last vertex. I still have a good ordering of the first n minus 1 vertices. Okay. Okay, so this ordering still gives one of these greedy orderings in a slightly smaller graph. Okay. Alright, so if I look at lambda Vn minus 1, Vn minus 2, right? This is the maximum number of paths from Vn minus 1 to Vn minus 2. It's the size of the maximum flow from Vn minus 1 to Vn minus 2. When I deleted this last vertex Vn, that might kill off some of the paths. It's not going to create more paths. Okay? So this is, what I'm saying is that when I delete when I delete a vertex, the max flow is not going to go down. Sorry, it's not going to go up. Okay? So deleting that last vertex is not going to improve the max flow. Okay? And okay, by induction, I know that the connectivity between these two vertices, right, because this is an MA order, is given by the singleton cut of Vn minus 1. Okay? So this is A. Okay? And now, because in my original ordering, Vn minus 1 was chosen before Vn, A was at least B. So that's one side of our triangle inequality. Okay, so we checked off this one. Now we will do that one. Okay. And we'll do something similar. Okay. So last time I said, oh, imagine you got rid of the last vertex, you still have an ordering of the first n minus 1. The same would apply if I got rid of the second to last vertex. Right? So if I got rid of Vn minus 1, Vn would still come last. Okay? So again, I have that I still have an ordering in the graph obtained by deleting the second to last vertex this time. Okay. So now we do the same thing. Okay. The connectivity between n minus 2 and n. Okay. The connectivity is not going to go up by getting rid of Vn minus 1 because that only hurts your flow, if anything. Okay. And these two are, again, the last two vertices in that maximum adjacency ordering. So by induction, it's B. All right, so okay, so that where was I? Okay, good. So we got this thing is at least b, this thing is at least b. Okay, so we're able to check off this case where c was equal to 0. Okay, we're almost done. It's very subtle. Okay, so going back to our original setup, we figured out the c equals 0 case. Now I just have to deal with c bigger than 0. Okay. Again, I want to show that Vn by itself gives the minimum Vn minus 1 cut. Okay. All right. Okay, so to do this last c greater than 0 case, I'm going to reduce to the c equal to 0 case. Okay. So let's let G0 denote the graph, where I pretend to delete this edge. Okay. I just delete the edge directly from Vn minus 1 and Vn, which gives us the case we just studied. We know how to handle c equals 0. Okay. And the key point is that deleting that last edge doesn't hurt this ordering thingy. Vn minus 1 would still come before Vn. The ordering would still stay the exact same. You'd have the same maximum adjacency ordering in G0. Okay. That's important. So now we have, okay, so when I'm looking at the minimum Vn minus 1 Vn cut, and I delete an edge of weight 5 in between. That edge always had to be in the cut, right? You can't avoid any edge between these two things. So the cut will go down exactly by 5 in that case. Okay? So it'll be the connectivity in this smaller graph plus c. Exactly. Okay, so, and we've already analyzed the c equals 0 case, which would have given us b. Okay. All right, so that is the funny proof. Somehow we did these manipulations like removing one vertex at a time and looking at that hypothetical, but that allows us to do some induction or something. Okay, and we're able to show that in fact the connectivity between those last two vertices is the degree of Vn. Okay, it's probably the most indirect proof we've done together. We've proven in mathematically, but it's still kind of not clear. Right, so we're really leveraging induction to do a lot of work for us. Okay, so so that establishes that Vn does give you the minimum Vn minus 1 Vn cut, and that this kind of absurd algorithm, which just orders things in this greedy maximum adjacency ordering and kind of keeps contracting the last two vertices, somehow produces the minimum global cut much faster than actually we know how to compute a single ST cut. So actually historically this was significant because before this algorithm we didn't think that ST cut was going to be harder than global minimum cut. Okay. Yeah, right? So after this algorithm, global minimum cut actually looks easier than one pair's minimum cut. Somehow we're leveraging some more symmetry. Okay. All right, that was a long analysis. All right, then I will go more quickly through the second part. Okay, and what details I don't quite cover will be explained in greater detail in the notes. There will be some stuff you can still black box. Okay? Alright, so the global minimum cut, we did some clever algorithm. Now let's talk about edge disjoint paths, or really max flow and unweighted undirected graphs. And it's going to introduce this idea called sparsification, which is really a much more general idea, although it's partly inspired by this algorithm. This would be an early example of sparsification. Okay, so what's the high-level idea? This doesn't have to just be for graphs, but I'll talk about graphs. You're given a big graph. Okay? Too big to do much computation with. Okay? And what we'd like to do is, for some problem of interest, okay, I would like to find a much smaller graph H, one with much fewer edges, to somehow preserve some structure for the sake of some problem I'm interested in. It's sort of like compressing, sort of like figuring out which details I can leave out. Okay? But it's in general a very interesting idea, the idea of taking your big input, instead of just solving your problem right away, trying to find a smaller graph and then solve it on that. And then, your algorithm would just be faster because you're working with fewer edges. Okay, so that's called sparsification. And this idea has, of course, gone way beyond graphs. Now, just in general, you're given something with a lot of data and you would love to have a much smaller representative data set that preserves the structure of the problem. Okay, so you can think of this as a clean example of a much broader strategy. Okay, so here's one that you guys already know. Suppose that desired property was reachability. Okay, so you get a graph. And I say, find me a subgraph that preserves reachability between pairs. So this is an undirected graph. Okay, so find me a graph H that has, I guess at most n edges, or something much smaller than, say, n squared. Imagine G had n squared originally. Find me a graph that is much smaller than that, but it will preserve reachability in the sense that two vertices are connected in the original graph, if and only if they're connected in the smaller graph with, say, closer to n edges. I mean, that would be very appealing, right? Because that would summarize, who is connected to who. But in much fewer than, in the worst case, n squared edges. Okay, so, let you guys think about it. How can I come up with a quote-unquote sparsifier to preserve reachability? Yeah?
A lot of strongly connected components, and then make it more modular.
Oh, okay, that's also interesting, but this is even an undirected graph. So I guess everything is one strongly connected component. How would you even summarize a strongly connected component, I guess, in that lingo? Yeah?
Would you essentially be finding a spanning tree for this?
Yeah, a spanning tree or a spanning forest in case the graph wasn't connected, right? Let's say the graph is connected. Then the spanning tree will be a connected graph, and it's a subgraph, and the spanning tree alone will tell you who's connected to who, which is, I guess, everyone. Right? But it only has n edges, or n minus 1 edges. Okay, so by computing a spanning forest of your original graph, you can summarize all the connectivity, the reachability information, but have much fewer edges. Right? It's a very common application of spanning trees. Okay, so we're going to do something a little bit more ambitious, but sort of similar in spirit. So you can think of spanning trees as doing k equals 1. So I want to preserve all connectivities up to some parameter k. So let's say k is 10. Okay. I want to find a graph with relatively few vertices with the following property. So h should be much smaller than g. What I want to kind of say is that two pairs S and T have connectivity 10, there's at least 10 edge disjoint paths in the original graph, if and only if they have at least 10 edge disjoint paths in a much smaller graph. Okay, so, or more generally, if my parameter is 10, but ST actually had connectivity 5 originally, I want them to still have connectivity 5 in the original graph. Okay, so that's what this is saying. So, because it's a subgraph, the connectivities aren't going to go up. They're only going to go down, if anything. Right, I'm only dropping some edges. That's going to hurt some connectivities. But I want to make sure that the connectivity is at least a minimum of my parameter k in its original connectivity. So if the original connectivity was 5, you're not going to get up to 10, of course, but you would like to still have connectivity 5 in your smaller graph. But maybe if somebody had connectivity 100, you don't really care if there's 100 connections. You just want to know if they have 10 connections, and maybe you can find a smaller graph to summarize this information. So the spanning tree would be k equal 1. K equal 1 is just preserving reachability. Edge connectivity 1 is one path. Okay, so this too is practical and useful. So often we're just interested in kind of a moderate enough connectivity, which is a little more robust than one path, and we don't really care if there's some pairs that have, tremendous connectivity beyond the minimum. Okay. All right. So, actually, maybe I'll ask briefly. We have a little time. Say k equal 2. Does anyone have any idea? So k equal 1, we can do one spanning forest, and that'll tell me whose has connectivity 1. If I wanted to do connectivity 2, or 1 and 2, any ideas? General, yeah.
Can you do some sort of thing where you remove one of the spanning trees and then try to find another one?
Yeah, so natural strategy is find a spanning tree first. That'll address everyone that's 1. Take it out of the graph, and then find another spanning tree or spanning forest. Okay. If you do that, you only have at most 2 edges. So that's good. Okay, so that's exactly the algorithm we're going to study. Okay, sometimes it's called a greedy forest packing. Okay. So we'll just keep doing it ad infinitum. I guess you can stop at a particular k if you're only interested in k, but okay, so that's exactly the strategy that's on the projection. I'm just repeatedly ripping out spanning forests of the remaining graph until there's no graph left. Momentarily we'll discuss how to do that a little bit faster in some clever ways. Okay. But, we're just trying to take as big a forest as possible, as big a forest as possible, as big a forest as possible. Okay, makes sense. Okay, so so the claim is that the first 2 forests are going to preserve connectivities up to 2. The first 5 forests will preserve connectivities up to 5. The first k forest will preserve connectivities up to k. Okay. Okay, I gave myself a little space for an example. I'll do it. I'll just do it since. Okay, so the first forest, might be something like that on the left. That will be one spanning forest of the original graph, if I'm not mistaken. Okay, so that means those edges are now unavailable for the next forest. So that should leave that. Okay, and I just want a spanning forest of this graph, like that. Okay, so that would be a second forest, and the third forest, I guess, would just leave these 2 unused edges. Okay, so we've taken the input graph and turned it into 2 forests. And I guess the interesting part of the claim, let me draw this. So the original graph had min cut 2, right? Remember that, that's the 2 edges in the middle. Now the claim is saying that if I looked at just the union of the first 2 forests. Okay, so here's F1 union F2. That should preserve. Every vertex should have connectivity at least 2 in this graph. The minimum cut should be at least 2. Which I think is true. I think between any 2 vertices, you'll find 2 edge disjoint paths between them in the union of the first 2 forests. And it must be true because we're about to prove it. Okay, but I think upon inspection it's also true. Okay, so it's kind of a neat idea. Alright, so what's going on here? Alright, okay, so let's prove this idea that the first K forest will preserve connectivities up to size K. Okay. This is what I alluded to earlier in terms of kind of spanning trees and connectivity clashing together. Alright, so here then is the lemma. If I have some cut, okay, and it has at least K edges, then the claim is that if I look at just the first K forest, those K forests will have at least K edges from that cut. Okay, so I drew a circle around the set of vertices S. Okay. Okay, so let's prove this. I'll keep it moving since we have about 10 minutes left. Okay, so suppose not. Right, so suppose C had at least K edges, but in the first K forests, the K forest took less than K of them. Maybe K is 10. So C has 10 edges, and the first 10 forests only took 9 or less of them. Okay, so if not, there's some edge that's left out, right? So let's let E be an edge that's not in the first K forest. Okay. Now, so E is a particular edge. Now each forest was a spanning forest, right? So if E is not in the first forest, it must at least be spanned by F1. If E is not in the second forest, it's still spanned by F2. Okay? So that means the endpoints of E are already connected by each of those forests. It's the definition of span. So one forest might look like this, but the point is that it connects the endpoints of E. Okay? But that implies, that there's no way to draw that forest without going over the boundary, without using an edge from the cut. So that forest must have at least one edge. Okay, so as soon as I've omitted one edge from the cut, I now know that all the forest that omit it is using some other edge from the cut. Okay? So every forest has at least one edge, in which case you'll end up with at least K edges over K forests. Okay. All right. Sorry. Okay, so now that we have that, okay, the theorem follows pretty easily. So if I'm looking at the first K forest, I want to know the connectivity between S and T. If the minimum cut between S and T was greater than or equal to K before, right, then it's always going to have at least K, then each cut has at least K edges. Okay, so let's say that the minimum cut was already greater than or equal to K. Okay. So all ST cuts, I'll call it C, have by definition at least K edges. Okay. And what we just showed is that C and H has to have at least k edges. That's what we showed in the lemma. Okay, so we'll preserve any cut of size at least k. Now, if the connectivity was less than k, if it was k minus 1, then I know that it's going to have connectivity k minus 1 in the first k minus 1 forests, and the kth forest only helps. That's where the min comes in. Okay. Alright, so we're preserving all the cuts with these forests up to a certain size. Okay. So that works. Alright, so we have about 5 minutes. So let's talk a little bit about how to compute these things and also why they're useful, somewhat briefly. If I were to sort of run this algorithm as described, how long might this take? Maybe close to like m squared or something, or m squared log n. It sort of feels like a bunch of minimum spanning tree type of algorithms, one after another, until the graph disappears. I guess in the worst case, you take one edge at a time. Okay, so maybe like m squared log n, or something more clever from the homework or whatever. Okay, something close to m squared. Okay. Very quickly, does anyone want to suggest a faster way to implicitly do this? We now know this is useful, this preserves cuts, but it's a little bit slow. M squared time is a little bit slow. Okay, so we're going to do something a little bit closer to m, like m log n or something. Alright, so if you think about imagine going through the edges one by one, and starting with just a bunch of empty forests. Okay? You want to make sure that F1 is a spanning forest, and F2 spans all the remaining edges, and F3 spans all the remaining edges, F4 spans all the, I should have gone this way. Okay? So if you take a particular edge, find the first forest it fits into, which for the first edge will be F1. Find the first forest that doesn't span it, and add it. Go to the second edge, find the first forest that doesn't span it, and add it. Third edge, keep finding the first forest that doesn't already connect the endpoints of an edge, and just add it there. Okay? Then you'll end up with a property again, that the first forest is spanning, right? Because anyone it turned down was spanned. Of the remaining edges, F2 is spanning, since everyone it turned down was spanned, and so forth. Okay, so you could do a first fit kind of construction. Okay, that's appealing. But how can I make this approach really fast? So I have an edge, I want to find the first forest it fits into. You could start at F1 and scan through. I'm saying maybe you could do better than scanning. Yeah. We can binary search. We can binary search and find the first forest it fits into. Okay? And then maybe we can also do a disjoint union to keep track of the tree, so you can quickly figure out if it's spanned or not. Okay, so some binary search plus some data structures. Will get you m log n times, that crazy thing that shows up as a disjoint union data structure called the inverse Ackermann, which is much smaller than log n. Can you do even better? Okay. It turns out the answer is yes, but I won't have time to go through the details. You can do this in OM time. Okay, but what's really cool is you actually somehow leverage those maximum adjacency orderings that we discussed from the minimum cut algorithm. I'll go over briefly in what time remains. Okay? Now, okay. let me first explain one particular case where this is very, yeah.
What was the runtime of binary search?
M log n times alpha mn, which represents the inverse Ackermann function. So the disjoint union has this very slow growing additional factor. I think alpha mn, where m and n are roughly the size of the universe, is like 6, so it's pretty small. Okay. Let me explain one very practical use. Now we know we can pack these forests really fast. You could do m log n just doing binary search, and you can even do m with, it's actually a pretty simple algorithm, but again very subtle, using those adjacency orderings from before. So roughly you can get these forests for free. You can get all the forests in linear time. Okay, so what's one basic case? So remember, when we run ST max flow in an unweighted graph, I just find one path at a time, one path at a time, one path at a time. Right, this is a Ford-Fulkerson algorithm, the augmenting path algorithm. Okay? That means that, at the beginning from S to T, you're just trying to find one path. Right? And it seems like sort of a waste of time to look through use the whole graph to find one path. You should just use the first forest. If there is a path, the first forest will contain it. Okay? Now, suppose you want to find a second path. You're trying to figure out if S and T have connectivity too. Okay? You already have the residual graph in the first forest. And to guarantee connectivity too, throw in the edges from the second forest onto your current residual graph. Right? And that's a much smaller graph to find the path in. Okay, so in general, in the kth iteration, this only works in undirected graphs. Only use the first k forests, updating the residual graph appropriately to find the kth iteration. Okay? The advantage is that the kth iteration only takes n times k time, because you're just running BFS or whatever algorithm in a much smaller graph. It's in the union of k forests. Okay? As a result, you end up with a Ford-Fulkerson type of running time, except now it'll take you m plus n lambda squared. M is just to build the forest. N lambda squared is just what you get from 1 plus 2 plus 3 plus 4, and so forth. Okay, so you can actually kind of improve Ford-Fulkerson in dense graphs with this idea. Okay, so I only mentioned that the idea for computing the forest is sort of slick. You do one maximum adjacency ordering of the graph, okay? And somehow, so you have V1 through Vn, and you go through the vertices V1 through Vn, j equal 1 to n, and then in the first forest, so Vj has some edges to preceding vertices in the list, and you're going to put the first one in the first forest. So this edge will go into F1, this edge will go into F2, this edge will go into F3, and so forth. So somehow you insert the edges in this particular order, and then you can argue that sort of a subtle analysis like we did for minimum cut, this will also give you a greedy forest packing. So the algorithm itself is very simple because you just order the vertices and then you follow these instructions. The analysis also is not like crazy, but you have to be careful and you use some induction and stuff like that. Okay, so that's all. Next time we'll talk about matches.